Yeah.
We have the pleasure of having with us today Professor Abdus Salam, who is one of the most distinguished scientists of our times. He is the director of International Center for Theoretical Physics in Trieste, which in fact he founded. He's been professor, continues to be a visiting professor at the Imperial College London. He's of course Nobel laureate in physics, very well known in this part of the world. Professor Salam has been going around the country talking to scientists, academics, people interested in cultural activities, arguing with us about all kinds of things. And so we thought it would be a good idea to get Professor Salam here and tell us a little bit about this tremendous excitement in physics which is happening these days. Professor Salam, you have yourself taken part in this big revolution which has occurred in physics and continues to occur. Why do you think physics is so exciting, and where is it going?
You see, physics has been transformed. Particle physics we are talking about has been transformed since, I should say, the middle of the 70s. We did not have, before the present excitement, any coherent set of theoretical ideas which would combine the various types of, which would give a direction to the subject. Fortunately, the work of the 70s, the work which started in fact in the 50s but culminated in the 60s in formulating a precise theory, and that theory was tested and found to be correct in the 70s, particularly towards the end of the 70s.
You're referring to electroweak? Yeah.
That gave a direction which is now embodied in what's called the standard model of particle physics. The standard model says that all matter is made up either of quarks, all the hadron, protons and neutrons are made up of quarks, or it's made up of leptons, electrons and neutrinos, or muons and their others, and so forth. So we enumerate 45 particles, still a large number.
Yes.
Make them into 3 families of 15 each, which we say are the fundamental building blocks.
Well, you know, somebody who's not right into the middle of physics, he says, so what? So what's so great about this?
Well, what's so great about it is, I haven't finished yet, but can I just finish the standard model? The standard model then goes on to say that the 4 fundamental forces of nature are mediated by a set of 13 particles which go between, which are messengers of these forces. Now this totality of 45 plus 13 plus 1 more particle, the so-called Higgs, 14 particles, 59 altogether, makes up for all forces of nature whatsoever.
The forces being gravity, the force which keeps the nucleus together, nuclear forces, and the force of electric force, electromagnetic force, which is between charges.
And the fourth force is the one which... The weak nuclear force which is responsible for radioactivity.
That's right.
Now these 4 forces constitute all the forces we know of, all the 4 forces which from the beginning of the universe till today have determined what the universe looks like, what we are made of, what makes the earth what it is, a habitable place. So if this is called the theory of everything.
Yes.
If you have a theory of everything expressed in terms of quarks, leptons, and these fundamental 4 forces, I think it's a great triumph for human mind.
Theory of everything, but not necessarily a deterministic theory that everything was decided the first day.
No. That's a separate principle, the principle of quantum theory, which is overriding over the entire business. Now, this is the transformation which has occurred, as I said, in the 70s, towards the end particularly. 78 was the last experiment. which established the indirect nature of the correctness of our ideas. Then in 82 and 83, the particles which were missing in this whole scheme, the W and the Z particles, W plus, W minus and the Z0, 3 particles, were actually made in the laboratory for the first time by Rubia and van der Meer, who got a Nobel Prize in 1984 for this discovery.
Even the masses of these particles were almost predicted, isn't it?
Well, that's the point. You see, our theory predicted the masses of these particles, and they looked precisely at those energies. The point was to have accelerators which should have those energies. No such accelerator existed before van der Meer and Rubia got to the business. Afterwards, when the accelerators were made, they looked precisely at the mass values which we had predicted and found them. And so everything was confirmed. Now, the question now arises, what happens next? And that is where we come in now. You may say, well, 45 to us is too large a number. Can we reduce it still further? Can we reduce from 4 forces we have reduced them to 3. Electroweak force is the force which is a combination of the weak nuclear force plus the electromagnetic force. The other 2 forces, the strong nuclear force and the gravitational force, stand outside this joining together. Why? That's the question.
So, how are things going?
Well, things are not going well for 2 reasons. First of all, we need a still larger accelerator. Some are being made already. For example, at the Stanford Linear Accelerator Laboratory, they are making an accelerator which will make Zs very copiously. This will not find anything new, but it will make Zs a few times.
Incidentally, these are particles which have masses something like 70, 80 times the mass of the proton.
Like nuclei. They are very, very heavy particles. Called elementary particles in the act of faith, if you like. Now, what they will do with this Z part, this will come about in 87, towards the end of 87, this accelerator, the Stanford Linear Accelerator. It's end of 87.
The way particle physics or physics works now, is this true that theoretical ideas provide you many, many choices?
Correct.
And it's experiment which has to determine which is maybe the correct one and how to go further.
Correct. We would like to change it, of course. We would like to have everything predeterministic, like Einstein did with the relativity theory. But we are now faced with, at the moment, too big a task. We are trying to explain much more than Einstein did. We want to comprehend his theory as a simple, humble part of our theory.
But we haven't yet got a resonance with nature to say nature must really go this way rather than this way.
Well, that's what we would like to have. Well, that's the end of the theory. But may I just go on for a minute or to say what we are hoping to achieve in the chronological order? You see, as I said, we haven't got the accelerators, and these 2 accelerators, one at Geneva, which is 27 kilometers in circumference, 27 kilometers of tunnel, which you were explaining quite rightly to the Prime Minister this morning. That tunnel is being completed, and it will come, as you said quite rightly, from the tunneling from 2 sides, it will come together to 1 millimeter. That's being done with laser accelerators, laser things. Now, that tunnel is being constructed under the mountains of Jura, and that will be ready in 1989, from 3 years from now.
You need a large diameter tunnel because these high energy particles have to be bent around to come back, and magnetic fields essentially.
But the trouble is that the electrons, if they are very fast, emit radiation so much that you will need to pump so much energy into it that Geneva does not have. So the larger the tunnel, the better.
Because once they bend at a smaller rate, they radiate less.
Exactly. So these accelerators will be ready in the 1990s and will answer questions about the correctness of our theory to 1/10% accuracy rather than 1% accuracy. The hope is